All right, we're going to pick up here with our multi-service system, and we're going to look at an example. It's called the Draper Clinic problem. It's problem 5.17 on page 218 of your textbook. And let me read that to you. It's a very short problem statement. The Draper Clinic has 2 general practitioners who see patients daily. An average of 6.5 patients arrive at the clinic per hour, Poisson distributed. Each doctor spends an average of 15 minutes exponentially distributed with the patient. The patients wait in a waiting area until one of the 2 doctors is able to see them. However, since patients typically do not feel well when they come to the clinic, the doctors do not believe it is good practice to have a patient wait longer than an average of 20 minutes. Should this clinic add a 3rd doctor? And if so, will he or she alleviate this waiting problem? So that's the Draper Clinic problem. So what you should do with each of these problems at the outset, even though they are really example problems, they're somewhat contrived, you need to try to get an idea physically in your mind what this problem looks like and what we're trying to solve for. So let's try to describe what this Draper Clinic looks like. So first of all, what you should ask, how many doctors does it have? And based on the problem statement, the very first sentence says the Draper Clinic has 2 general practitioners, so who see patients. So who are the servers and who are our customers? And hopefully in this situation, you can see that we have 2 servers who are our doctors, who are MDs. Okay, so we have 2 servers, again, more than one. What does this clinic look like? Well, let's hypothetically diagram this clinic. Here's the office area, and somewhere in the office there's going to be 2 exam rooms. There's going to be exam room for physician number 1 and exam room for physician number 2, and then somewhere out here there's going to be a waiting area. And so here, this is again a crude diagram. These are our chairs for the patients waiting to get in to see the doctors. Now at this point you should ask yourself, does this satisfy all of our criteria for using the analysis? And one of the things I'd like to talk about is the size of the waiting room. Now there's no doctor's office that's infinite in size, but on the other hand, the question is, are there enough chairs? Are there ever so many customers that arrive that will fill up the waiting room to the point where customers will not enter the waiting room? And the answer in this case is, we'll have to say, is no, because that's going to be the assumption of our so we can do the work in the analysis. The next thing you should ask yourself is, for our servers, for our doctors, what's the arrival rate, what's the service rate? And for our patients, what is the arrival rate? And we're told an average of 6.5 patients arrive at the clinic per hour. So our arrival rate is 6.5 patients per hour. And we're also told that it takes a doctor, on average, 15 minutes to see each patient. Well, there's 2 problems here in trying to determine what mu is. First of all, in terms of minutes. And so right away, you need to recognize that either the minutes needs to be converted to hours, or the hours in the arrival rate needs to be converted to minutes. And in this case, it's probably more straightforward to think about this being converted from minutes to hours. The next thing that you should notice is the following, that this is 15 minutes per patient is not a rate. So it's not a rate. What we want to have this is patients, and convert this to patients per hour, just like our arrival is in terms of patients per hour. That it has to be expressed in this rate. So what I would encourage you to do at this point, perhaps the easiest way to think about this is, if doctor can see one patient every 15 minutes, how many patients does the doctor see per hour? And of course, that's 4, because there's 60 minutes in an hour, and he sees one patient every 15 minutes. So the service rate is 4 per hour. This is an area right off the bat where students are going to make errors. So be very careful about this, expressed as a rate. This is, again, 4 patients per hour. There's one other thing I want to mention, and that's the following. Let's think about this. All right, so we've said now that lambda equals 6.5 patients per hour, and mu equals 4 patients per hour. But wait a minute. Didn't we say, what did we say in the last lesson? What the relationship between lambda and mu? Didn't we say lambda has to be less than mu? Yes, and we did for the case where the server is 1. Mu has to be greater than lambda. But in this case, we've got multiple servers, so the relationship that has to be satisfied, which it is here, is lambda has to be strictly less than S times mu, or the number of servers. And think of this as your effective service rate. So in this case, we have the arrival rate is 6.5, but we have 2 doctors, each serving at a rate of 4 per hour. So our effective service rate of those 2 doctors is 8. And so, of course, 8 is greater than 6.5. So in that situation, we're good to go. All right. So let's begin to think about our problem on the next slide. So the question that you really want to answer, let me reread this. Since the patients typically do not feel well when they come to the clinic, the doctors do not believe it is a good practice to have a patient wait longer than an average of 20 minutes. So the question we need to answer is, do the patients wait longer than 20 minutes to see one of the doctors? And if so, should the clinic hire a 3rd doctor? Right, so those are the 2 questions that we need to answer. And the first question is the one that we're going to deal with right out of the gate. Do the patients wait longer than 20 minutes to see one of the doctors? So the question now we should ask yourself, which one of the operating characteristics should we find? Is it the number, or is it the time, or is it the probability? And so hopefully you see right away it's the time, because we're talking, do they wait longer than 20 minutes? And so at the time, do we need to find W or W sub Q? Which one of those do we need to find? Well, they're waiting to see one of the doctors. So this is the time, the waiting time in line. So we need to find WQ. And we're going to go to our table that's on page, the table that's on page 215. And we're going to look under, on the right-hand column, under the multiple server model, for the formula for W sub Q. And what we're going to find is that WQ, and we're going to use the, actually not the formula that's in the text, but we're going to use Little's formula. WQ is going to be L sub Q divided by lambda. So now let's go forward. So now we know what the value of lambda is. We have 6.5 per hour. We know that mu is, we're having 4. The service rate is for each doctor is 4 per hour, and we have S equal 2. And now we want to find W sub Q, which is LQ over lambda. But wait a minute, we don't know yet what L sub Q is. So now we need to find L sub Q. And it turns out, if we look at that, L sub Q on page 215, L sub Q is going to equal to L minus lambda over mu. But we still have a dilemma, because now we still don't know what is L. And it turns out that the formula for L is, we'll see on the next slide. This is the formula for L. And let me go through it. It looks a little messy, but it's not that hard. It's there's really 3 terms. There's a term, there's a quotient here, which is, the numerator is lambda times mu times mu divided by, lambda divided by mu raised to the S power. The denominator is S minus 1 factorial. Again, hopefully you remember what that factorial is. In other words, again, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. And again, you should have a function on your calculator that'll compute that function. And then so S minus 1 factorial times S times mu minus lambda and the whole quantity squared. One of the things I want to point out here too is this term is always squared. It's not S. In this case, it's going to look the same. In our formula, when we compute this, S is going to be 2. But that's not always the case. But this is always squared. And then finally, our next term is P sub 0. And you remember what P sub 0 is. It's the probability that there's no customers in the system. And then the last term is plus lambda over mu. We think we're close, but wait a minute now, where there's still a term that we don't know, and that's P sub 0. So how do we calculate P sub 0? And that's what we're going to see on the next slide. And P sub 0, before we get P sub 0, I'm going to do a little algebra. And if you remember what we wrote last time, L sub Q is this term. But notice this is L minus, let me erase this. What we want to really get to is we want to calculate L sub Q. But in order to calculate L sub Q, we have to calculate this value. And of course, what I'm going to do next is just a little algebra. Remember, this term is L. All I'm going to do is place this term in these brackets here, substituting for L. So this term is L. And then I'm going to subtract, let me use a different color. I'm going to subtract lambda over mu from L. So actually, let me erase all of that. Actually, this is, again, this term is L, and this term is the same term, minus lambda over mu. So what this leaves is just this portion, and this term ends up being L sub Q. So we can save us a step of computation by doing a little algebra. So, but we still need P sub 0. And so now let's see what P sub 0 is. And P sub 0 is this term, and we're going to talk about that and work through that very carefully. And it's a first term is a term of sums, and then we'll talk about this symbol is a summation symbol. And then this term is again fairly straightforward. It's a product of 3 terms, and then that's all taken to the negative to the -1 power. And if you remember, what does that mean? In other words, if you have a term a to the -1, what's that the equivalent of? This is 1. This is same as saying the inverse of a, 1 over a. Okay, so the other thing that we're going to do now is the first thing that we're going to do on the next slides. We're going to calculate first P sub 0. Then we're going to, and remember that this term here is L sub Q. We're going, not L sub G, L sub Q. And then we're going to, once we calculate P sub 0, we're going to substitute that into this equation, calculate L sub Q. Then once we calculate L sub Q, we're going to go back and put that in this equation, and we're going to end up with W sub Q, and then you're going to use W sub Q to answer this first question, W sub Q longer than 20 minutes. So that's the process that we're going to follow. So let's begin that. Now, I want you to know my writing is going to be, these are complicated formulas. My writing is going to be a little bit messy, but what I want you to do is to think about, and I'll have this all summarized on the last slide so that you can see how this works and see where we get the results from. All right. So the first thing is we know that our S is 2. We know that lambda is 6.5. And we know that mu is 4. All right. So that's where we have to start. And so for P sub 0, the first term is as follows. The first term, and I'm going to, is going to be the sum for n. N is just an index and has really not much to do with the problem. It only has to do with the sum from n equals 0 all the way up to s. Let me begin this again. Sorry about that. 6.5, 4. We're going to make a sum for n equals 0 to s minus 1. And this, what we're going to sum is this term 1 over n factorial times lambda over mu, and that raised to the nth power. Now, and then we have another term. I'm not going to write that term out yet. I'm just going to concentrate on this first term. Then we have another term that's three things over here, and then eventually we're going to take the inverse of all of this. But first thing I want to do is focus on this term. Now this term is a sum. It's the Greek letter sigma, and it stands for a sum. And now we can begin to substitute in, and we know that our s equals 2, and so we can find out what this term, and what is s minus 1. This is going to equal, since s is 2, this is going to equal 1. And so what that means, this is two terms. There's two terms in this sum. There's a term for n equals 0, and then we count up and we go to n equals 1, and that's when we stop. And so if we had 3 servers, there would be 2 terms, because we would start at 0 and we would count up to 2. So there would be a term for n equals 0, n equal 1, and n equal 2. But for this case, there's only 2 terms. And the first term is the case where n equals 0. So that's 1 over 0 factorial times, and I'm just going to use lambda over mu. And that's going to be to the 0 power plus, and then it's a sum. There's another term, 1 over 1 factorial times lambda over mu raised to the first power. And that's the 2 terms we've just substituted in. N equals 0 into these terms, both here and here. And also then n equal 1 for the second term to here and here. Okay. Now let's look at this. Let's look at this term and remember some things. What's the definition of 0 factorial is 1. So 1 over 1 is 1. And anything raised to the 0 power is 1. So this term is, first term is 1 plus, again, 1 over 1 factorial is 1 times itself, and so that's 1. So this is 1, and lambda over mu to the first power is just lambda over mu. And so if we do that division, we know, let's see, let me put it over here, lambda over mu, lambda divided by mu, this is a term you may want to keep, is 6.5 divided by 4, which is 1.625. So this term then reduces to 1.625. And then we're going to add to that this term here. Now this term, third term, consists of 3 products. And the first product is 1 over s factorial. The second term is lambda or mu, that quantity to the s power, or and then the third term is s times mu over s times mu minus lambda. So that's the third term. And so we're going to substitute in here. 1 over s factorial is 1 over 2 factorial times lambda this term squared times the numerator now is 2s times mu, which is 4, all divided by 2 times 4 minus 6.5. And then eventually this whole term that we're going to get below is going to be, we're going to take the inverse of this. All right, so we've got this term, and now we're going to calculate these other terms. And so this is going to be 2 factorial is just 2, so this is 1/2 times 6.5 divided by 4 squared turns to be 2.641. And then this term, which is 8 over, go back and get another pen. This term then is 8 divided by 8 minus 6.5, which is 8 divided by 1.5, which is 5.33 repeating. And then we're going to take all of it, take the inverse of all of this. And again, I apologize for but I'll have this all summarized on a sheet on the last slide here. And so when we add these two terms then together become 2.625, and this last term, when you do all of this multiplication, is 7.042. We're going to take the inverse of that. Then this is finally when we add these two together, that's 7.669.667. Take the inverse of that, and this is going to be 0. In other words, this is 1 divided by 9.667. This is going to be 0.103. So now ask yourself, what is 1.103? And if you go all the way back, we're finding p sub 0. So this term is p sub 0. Wasn't that fun? And so what is P sub 0? What this means is there's a 10% chance that when you walk into the Draper Clinic that there will be nobody there. But there's a 90% chance that one or more people will be there. So that's how you can interpret that. All right, so let's go on now to the next, because we've found P sub 0. The next term that we're going to calculate is our term L sub Q. And L sub Q, we're going to use P sub 0, so we'll want to remember P sub 0, we've already done this work, is 0.103. And we know that L sub Q from our previous work is a formula that looks like this. It's first term is a ratio. It's lambda times mu times lambda divided by mu, quantity raised to the S power. And that's all over divided by S minus 1 quantity factorial times S times mu minus lambda. That quantity is squared, and then we're going to take this whole term and multiply it by P sub 0 to calculate LQ. All right, so let's substitute in. Remember, our arrival rate is 6.5. Our service rate is 4. Lambda is, again, 6.5. Lambda over mu is 6.5 divided by 4. S, remember, is 2, so that quantity is squared. Then the denominator is 2 minus 1 factorial times, whoops, that should be a parentheses, times 2s times 4 minus 6.5. And that quantity is squared. And then we're going to multiply this by P sub O, which is 0.103. When we do this arithmetic, we find out this numerator is, hopefully you can do this on the calculator, it's about as fast, 68.656. Denominator, again, remember 2 minus 1 factorial is just 1 factorial, which is 1. So this kind of goes away. And so this denominator is 1.5 squared, or 2.25. And then we're going to multiply this by 0.103. And when you do this arithmetic, lo and behold, this turns out to be 3.14. Now, again, at this point, ask yourself, what is 3.14? Well, 3.14, of course, is L sub Q. And that, if I asked you to interpret that, that's on average, there would be 3.14 customers or patients waiting in the Draper Clinic waiting room. So that means on average there's 5.14 in our system. Actually, that's not quite right, so disregard that. But because there's a time when there's none in the system, so the average is actually less than that. But on average, there would be 3.14 in our system. Excuse me, 3.14 in the waiting room. Sorry for that. All right, so now the next question is, what's W sub Q? And we know from our previous work, W sub Q is L sub Q divided by lambda. And of course, we know from the previous page, this is 3.14 divided by our lambda is arrival rate is 6.5. So W sub Q is 0.486. And again, at this point, you should ask yourself, what is this term? Well, this term is W sub Q, which is what we wanted to answer the question, but this is 0.486, but what's the units? Do you remember? Do you know how to answer that question? Well, the units for this term have to be the same units that we used for lambda and mu. And what time units? Remember, this was lambda was patients per hour. And the service rate was in terms of patients per hour. So the units for this term is hours. So this is 0.486 hours. So our customers wait almost half an hour, but how much exactly? And so in order to know exactly how many minutes we wait, we're going to multiply 60 minutes per hour times 0.486. And that tells us that this is like almost 30 minutes, but it's essentially 29 minutes. And so now we can go to our first question, which is 29 minutes. How does it compare to 20 minutes? Does it meet the doctor's standard? And the answer is no, it doesn't meet the doctor's standards. So then the next question is as follows. Should the clinic hire a third doctor? Well, wasn't that fun? How are we going to answer the quick question, should we hire a third doctor? Well, the answer is we're going to, in order to do this, we've got to go back and say, well, let's suppose we have S equals 3. And then we have the same arrival rate and we have the same service rate. Then for S equals 3 with the same arrival and the same service rate, what is WQ? Is it going to be less than 20 minutes? Let's go through all of that again. Hopefully you're scratching. Hopefully you're saying, oh no. Because this is this point that I want you to realize, you don't want to go through this and do this by hand. So let me jump out and show you this, how we're going to do this and make this work quite easy. And if you remember, and if you look at what we've done here, what information do we need in order to calculate W sub Q? Well, all we really need is S, we need lambda, and we need mu. Those are our only inputs. And there's a software developed that I pulled up for you and have made it available to you to use. There's a software available that will do this for you automatically. And let me jump out now. So I won't have to come back to, well, I will come back to this. Let me jump out now, and I want to show you this Excel software, and then we'll come back to this slide in just a minute. So and this application that I'm showing you is called Q Macros. And Q Macros is so cool. Here's the problem that we just have. And let me kind of take you for a quick tour. This software has several different models. And actually, this should be less than, typically less than 10, and this is not less than 8, but less than 11. And we have several different models. The one the one that's related to what we did in the previous lesson is this model. It's called the MM1, and the one that we're using for this lesson is called the MMS. And so we come over here to the MMS model, and all we need to input to this model is the arrival rates. We're going to just type in 6.5, the service rate, which is 4, and then the number of servers. And automatically, it prints out the data. And so if there are if there's 6 servers, it automatically prints out the data. If there's 2 servers, you can come down here. Let's see what we've already learned. First of all, if you notice, here's P sub 0, the probability that they're in the system. If you enter in here, if you enter 0 here, it tells you that that's P sub 0. If you were to enter 1, it automatically calculates P sub 1, 2, and so forth for you. So P sub 0 is 103 as calculated. And then we calculate, L sub Q. There's a little rounding error here. That's an error on our part, but it's 3.15, remember? And then finally, W sub Q. Here's the 4.8 hours, or 29 minutes. And I've just written a little, put in a little formula over here to convert the hours into minutes. And so our time, average time in the waiting is 29 minutes. So that information is all available to you just by entering those three values. And so now to answer our question, all we need to do is go in here and change, well, these are the outputs for our 2 servers. What about for 3 servers? And lo and behold, now we can go look at W sub Q, and all of a sudden it's 0.05 hours, or just 3 minutes. And so the question you need to ask yourself at this point is, should we hire a 3rd doctor? Well, the waiting time is only 3 minutes. That's good from the customer's perspective. But wait a minute, let's look at everything else that's involved here. Particularly, let's look at the server utilization. And in this case, you've got 3 doctors, all of whom are only busy 54% of the time. So now, let me pause here. I'm going to go back and finish with the slides here. But what I want you to see, and what I want you to go in, this is available on D2L. I want you to go back and experiment with this and see if you can make this work for you. Okay. But these are the terms that we're looking at. There's 3 minutes of waiting time. That's way less than 20. But there are some other questions that we need to have answered. So let me get out of this application, go back to my file, and we're going to go down to this last slide. And this is the summary slide for this problem. This is where we did all this work. You can follow this through. This is neatly presented, everything that we did on those previous slides. And notice what we just did, that our waiting time is 3.1 minutes. So even though this is really good, I'm still not sure whether or not the Draper Clinic should hire a third doctor, because there's, number one, is that cost effective? Is it cost effective to have the doctors very idle? So there's a lot more analysis needed, because it's really expensive to hire and outfit and insure a doctor. So that 29 minutes, maybe there's other ways in the process to improve the process to reduce that waiting time, but it may not be the most effective to hire another doctor. All right, and I'm going to talk a little bit more about that and a little bit more in the next part of this lesson, with other issues a couple other issues that are not in the textbook we need to be aware of.